All right, everybody. Well, tonight we're going to take a look at solving systems of linear inequalities. And this really isn't as scary as it sounds. Really, we're just going to take our newfound knowledge of linear inequalities, and we're going to take two or even three of them, bring them together, and take a look where all of their solutions overlap, and that will be our solutions for our linear inequalities. So really the key is, obviously, is to be able to set up your linear inequalities correctly. We'll take a look at a couple of different examples. We'll take a look at some word problems, and then we'll have plenty of time to practice tomorrow in class. So let's get started. So what does it mean to be a solution to a linear inequality? But basically what that means is that we're going to take two inequalities, and here you'll see we have a less than or equals to inequality, and here we have a greater than inequality, and these are the solutions for the individual inequalities. And so the solution is where they both fulfill the equation. So I have to be on this side of the line, and I have to be on this side of this line, but I have to fulfill both. So all of these areas right here fulfill both of those requirements. I'm a solution to this line, and I'm a solution to this line. So we'll just take a look at how that works in the real world and how that works as we're working through different problems. So, first question is the point 75 a solution to the following system? And just like we did with linear equations, where we had to check to see if it indeed worked for both equations, the same applies for linear inequalities. So 5 is greater than or equal to 7 minus 3. 5 is greater than or equal to 4. Check. 5 is greater than negative 7 plus 2. 5 is greater than negative 5. Is that true? Yes. So is this point a solution? Absolutely. It has to fulfill not only this inequality, but also this inequality. How about this? Is the point 8 negative 4 a solution? So y is negative 4 less than or equal to negative 2 times 8, negative 4 less than or equal to negative 16. Is negative 4 less than negative 16? Well, the answer to that is no. So is the point a solution? No. Do I even have to try this one? Absolutely not. It doesn't fulfill the requirement for this equation right here. Okay? All right, moving on. So, we are most probably going to see more of these types of equations. So the first thing we have to do, again, is we have to set up our equation, and so take a look at it. So here, when x is 0, y is 1, so there's 1 point. When y is 0, x is 2, so there's a second point. It looks like it's a equal to type problem. I've got my line, and now I have to figure out which way I'm going to shade. 0 plus 0 is less than 6. 0 is less than 6, so 0, 0 is a solution. And so I'm going to shade over here like this. And then my second equation is y is greater than 2/3 x minus 1. So I'm going to start at negative 1, and I'm going to go up to 1, 2 over 3, 1, 2, 3, up to over 3, 1, 2, 3. And I'm going to connect those dots. All right, because it is an inequality without the equals, we're going to make this dashed. Remember? Okay, so it's going to look something like that. And I apologize for how unstraight my line is. And then we have to test. Is 0 a solution? Is 0 greater than negative 1? Well, I think we'll agree that 0 is greater than negative 1. And so we have our lines coming down here. And what I want you to see is, where is the solution? Well, the solution is everywhere that complies with both equations. So these, all the way here to here, are solutions. Everything in the green shaded area is a solution. So we could say that negative 2, 0 is a solution. We could say that negative 2, negative 1 is a solution. We could say that negative 2, 1 is a solution. Anything over here is a possible solution to these two linear equations. Okay, x plus 6, so I'm going to go up to the 6. My slope is a positive 1. So my graph is going to look something like that. Check to make sure it's equal. 0 is greater than 6. Is that a true statement? I don't believe so. So my shading will look something like this. Okay. Next equation, negative 3. My slope is positive. I'm going to go up 1 over 1. Connect my dots. Looks something like that. Okay. Check to see my shading. 0. 0 is less than negative 3. Is 0 less than negative 3? I don't believe so, so my shading goes the opposite way. How many solutions do I have? No solutions. Okay. Okay. When we look at this one, we have plus 3. My slope is up 1 over 1. It's going to look something like this. Get my dashed line going. Something like that. Go to check my shading. 0 is less than 3. Agree. So my shading will come like this. Second equation is negative 1. So here my slope is 1. So up 1 over 1, up 1 over 1. Get my line. Something like that. Go to check my shading. 0 is greater than negative 1, so 0 is a solution. And this, you can see, starts to get really busy. So my solution runs right in the middle here. So my solution is only where I fulfill the requirements for both equations. Okay, if I'm on this line, I am not a solution. If I'm on this line, I am a solution. Okay, so you have to be very careful that you graph these correctly. Okay, and one last one to take a look at here. We have plus 1 and a slope of negative 1/3. 1, 1, 2, 3. Do my graph. 1, 2, 3, 1. So my graph looks something like that. Check my shading. 0 is greater than 1. That is not true. So I know that my shading has to go away from the 0. My second equation is negative 2. I have negative 2 down 1 over 3. 3 and 1 over 3. Okay. Graph. Excuse my point there. Hang on a second. Let me redo that. There we go. Okay. And then finally, 0. 0 is greater than negative 2. Well, again, This is a true statement. 0 is greater than -2, so my shading is going to go up like this. Where are my solutions? Well, they have to fulfill both of the inequalities. So my solution will be up here, because the first part of the shading of the second equation certainly does not fulfill. All right, let's do one word problem before we finish up the evening. So, D has at most $150 to spend on restocking dolls and trains at her toy store. Okay, so the most she can spend is less than or equal to $150. And she has $750 for dolls plus $5 for each train. She needs no more than 10 trains, so trains is less than or equal to 10. And she needs at least 8 dolls. So dolls is greater than or equal to 8. She needs at least 8 dolls. So let's take a look. When D is 0, when my dolls are 0, I have 5 into 150, I have 30. And when my T is 0, I have 750 into 150, my D is 20. So my first graph looks like, let me undo that. My first graph looks like this. My second equation is T is less than or equal to 10. T is less than or equal to 10. So it looks something like that. And I forgot to shade, so this is the first shade. T is less than or equal to 10. Looks something like this. And I'm not going to shade the rest because I'm looking for. And then D is greater than or equal to 8. So D is greater than or equal to 8. And since we're starting to get a little messy, I'm just going to color in everything that fulfills all 3 of these equations. So the question asks all the possible combinations. Well, looks like we could buy $10 and 3 trains, or $10 and 6 trains, $10 and 9 trains. We could do 12, etc., etc. Lots of different combinations as long as they fit inside of this area right here. So if this setup was a little quick, I want you to rewind and go back through it. I set up the first equation using the cost of the dolls and the cost of the train and the maximum amount of money I was allowed to use. The second equation is the limitation on she wants no more than 10 trains. And the third limitation is that she needs at least 8 dolls. And we have to fulfill all of those requirements. All right, there is no post video tonight. I do want you to go back through here, make sure you have good notes. We'll do plenty of practice on word problems tomorrow, and we'll see everybody tomorrow. Good night.